Senior Manager of Geospatial Analysis at Terra Carbon. We help develop forest carbon and other carbon projects. We do all the technical work. This session, probably unlike most of them, is actually going to be sequential, and it's reflecting the work that we have done over the past 2.5 years, trying to work on developing the methodology for jurisdictional REDD for Vera, now VM48, which has been released and is soon to be implemented once some of this work is finalized. So we'll talk about how all of the activity data is collected, as well as how the risk model is developed and allocated. And then at the very end, there will be a short, it was going to be a workshop, but now it's a shortened presentation on the implementation of the tool. So we will have time for questions after each session, and then we'll have hopefully time for maybe more questions at the very end when you put all of the pieces together. So with that, I'm going to hand it over to Gil Pontius.
Thank you, Becky. I am so pleased to see all of you at this session. This is a culmination of about 2.5 years of work where our group here has met through most of those 2 years, met nearly every week, and for about an hour and a half. And that's been the most satisfying, most intellectually intriguing part of my week for the last 2 years. It's been a really remarkable experience. I've been a professor at Clark University for 27 years, focused on GIS and land change modeling. And this is an application of land change modeling where money will exchange hands based on the outcomes of the model. So this is really where the rubber hits the road. So we've thought about the best way to organize the sequence, which is not the exact sequence in the program, but our first presenter will be Salvador Colon. He's a former professor of plant ecology and statistical methods, who's now a manager for REDD Technical Innovation at Vera, where he leads the development and evolution of protocols for REDD projects for the voluntary carbon market. Prior to joining Vera, Salvador served as Director General for Environmental Information and Statistics at Mexico's Ministry of the Environment, and then as Regional Coordinator for Latin America and the Caribbean of UNEP's Division of Early Warning and Assessment, and more recently as the Natural Resources Advisor at the Mexico Mission of the United States Agency for International Development. Salvador Colon.
Thank you, Gil. Hi, good afternoon. Could we put the first presentation, please? ¿Podemos poner la primera presentación, por favor? Sí, perfect. Yeah. Okay, so I'm Salvador. I'm going to tell you a little bit the REDD projects on the verified carbon standard, that's Vera. And then, okay, I think I don't need to tell you what I'm going to tell you. And perhaps I don't need to remind you that REDD stands for reducing greenhouse gas emissions from deforestation and forest degradation. I would rather tell you about REDD projects in general, and in particular within the voluntary carbon market. REDD project in general terms is a forest conservation project whose one of the main targets is reducing or avoiding, if possible, the greenhouse gas emissions that come from deforestation and forest degradation by implementing on-the-ground activities and interventions. Now, when a REDD project is carried out within the context of the voluntary carbon market, those emission reductions that are potentially or hopefully achieved by the project are meant to be traded, are meant to be sold, and then utilized by some other private, typically private sector polluters in order to offset those GHG emissions that they are unable or unfeasible to reduce or avoid. That way, through this market-based mechanism, financial resources are channeled from the private sector towards the landowners or forest owners, commonly in tropical developing countries, in order to protect the standing forests. Now, in order for these emissions reductions, in order for this market-based mechanism to work as it is intended to work, these emission reductions have to meet a number of very tough criteria. They have to be real, they have to be measurable, and they have to be additional, they have to be properly audited and verified, and they have to be transparent. In order to do that, then we do require some standardized protocols first for designing and implementing and monitoring the performance of those REDD projects. But also we need some rigorous standard procedures for quantifying the GHG emissions reductions that they achieve or do not achieve. That way, the fungibility of these emissions reductions, or all of this is necessary in order to ascertain to the extent possible the fungibility of those emission reductions, that 1 ton of CO2 equivalent that is avoided or reduced is effectively 1 ton of CO2 emissions that has been reduced anywhere. 1 ton is always 1 ton independently of where it happened. And that is the sort of the currency that is used in the voluntary carbon market. 1 ton of CO2 equivalent that is avoided or reduced is called a carbon credit. And particularly within Verra, a carbon credit is called a verified carbon unit after it passes through all the process of verification, quantification, and all that. But in principle, one verified carbon unit or 1 carbon credit should be equivalent to 1 ton of CO2 equivalent that has been avoided of being released to the atmosphere or sequestered from the atmosphere. And also, in order for this market-based approach work, then we also need to make sure that those carbon credits are not sold repeatedly and they are not used repeatedly. They are only sold once and they are only utilized once. We need a system, a proper, a very strict, very rigorous registry that keeps track of all those carbon credits. From the moment that they are issued in the project in the field up to the time when the emitter or the buyer utilizes them to offset their own emissions. That's why it was in that context that Verra and its flagship program, the Verified Carbon Standard, was created back then in 2010. And over the years, it has become the lead carbon registry in the voluntary carbon market. No need to talk about all the number of projects and all those countries that we have projects in. Over the course of the years, other similar or parallel carbon standards have been created, either internationally or in some particular countries like Ser Carbono, which originally was created in Colombia. And in particular, the first protocol, or as we call them, methodologies for REDD projects in Verra was created or was launched in 2010, which is what we call methodology VM7. And over the course of the years, since then, other similar or slightly different methodologies also for REDD projects were created in order to make them better fit different circumstances, different geographies, different deforestation patterns, and so on. As of today, we have, or until recently, we had 5 different or slightly different methodologies for REDD projects. Those 5 that are listed in there. Something that is really important and I want to emphasize is not going into the details of all these methodologies, but there are these 5 methodologies share some common traits that are very important for all these issues that we are trying to tackle. The development of these methodologies for REDD projects had to be created, in most cases, from scratch. There were no similar protocols for these sort of projects before BM7 in 2010. So that required a lot of research first, and also the development or adaptation of some concepts or statistical procedures or measurement procedures that were in there or were not in there and had to be created from scratch. For example, these projects, the project baseline, the reference region, the risk, how to assess the risk of non-permanence, and how to assess and account for leakage from those projects. There were a number of concepts and procedures that had to be developed in order to create these methodologies for these REDD projects. And let me elaborate a little bit on the first two concepts, the reference region and, the project baseline and the reference region, because these two concepts are key for REDD projects in particular. Unlike, and very, very tricky to implement in REDD projects in particular, unlike other type of projects like in clean energy, for example, or reforestation and so on. First, the project baseline is what would have happened in terms of degradation of deforestation in the project area in the absence of the project. And so, as you can see, in this case of REDD projects, the project baseline and the project itself are mutually exclusive. If you execute the project, then you cannot see that, you cannot observe the project baseline. And in order for you to calculate the project baseline, you cannot execute the project. So it's very, very hard to come up with a projection or estimation of the project baseline. So what do we do instead? For this project, the idea was to set up what is called the project's reference region, basically to identify and delineate an area that is surrounding or nearby the project area with which it shares similar physical, environmental, and socioeconomic characteristics, but which has been in the recent past exposed to the different agents of deforestation or forest degradation, unlike the project area. So basically the idea is what you observe in the reference region being very similar to the project area shows or somehow depicts what might happen in the project area if you don't do anything, in the business as usual scenario. And if you quantify the deforestation that has happened in the reference region, that will provide you a sort of approximation to the project's baseline. Let me show you how this works. Basically, you observe what has happened in the left part of the left side of the graph. You see the rhythm of deforestation and therefore emissions that have taken place in the recent past in the reference region, and then you measure that. You can measure that, and then you assume that the same trend might happen in the project area too in the future. For example, in this case, what you see in the historical data in the reference region show an increasing trend in deforestation and emissions. Therefore, you can see that if this trend continues, then the emissions and deforestation will continue increasingly. And you can project it, for example, using a simple linear model. That would constitute, provided all the similarities and all the requirements for the reference region are met, then that will give you an estimate or an idea of what the project's baseline might be. And so the project starts implementation in that point in time where the red line is, and then you monitor what happens in terms of deforestation in the project area. And what you observe is, I cannot point it out here, but this broken dark blue line is the deforestation that actually happened in the project area during project implementation. And you have to compare, or the efficacy, the performance of the project is judged by looking at that actual deforestation in the project area against what would have happened in the absence of the project baseline, the straight line in dark blue color. The difference between the two basically describes the climate benefits that the project has achieved, the emission reductions that the project has achieved. And these are translated after a number of considerations into the number of carbon credits that the project can claim, can sell, and then somebody can utilize. That's basically the idea. And as you can see, this is a pretty solid or pretty clear idea on how to implement and account for a REDD project, except for the fact that it leaves a number of considerations very open to the discretion of the project developer. For example, there is no easy way to set very strict requirements on how the reference region is identified and how it is delineated. And so the possibility exists, and that has been the case, that the project developer identifies some reference region that somehow shows a very high deforestation rate, and that will give you a very high baseline for your project, and that will lead to a very potentially a very high number of carbon credits. So that is an issue that cannot be easily solved. So starting in 2022, Verra launched an effort to basically first consolidate its various REDD methodologies that were in there, because in order to consolidate them and avoid confusion and differences between them, but also at the same time incorporating into this new consolidated methodology the latest developments and approaches for quantifying emission reductions in REDD projects. So, for example, we incorporated in this new methodology the latest centralized jurisdictional approach for setting baselines that also ensures that project baselines within the same jurisdiction fully nest within the jurisdictional baseline. And this has other advantages like providing internal consistency within among the projects within the same jurisdiction and more easily aligns the project outcomes with those that the jurisdictional government or the country government might be implementing through their participation in UNFCCC REDD programs, the Paris Agreement, and more easily fit them into their NDCs, for example. And some key features of this new methodology is that project developers no longer collect their jurisdiction, their deforestation data, and the project developers no longer delineate a reference region. Instead, now Verra takes over the responsibility of collecting high-quality, high-resolution deforestation data at the jurisdictional level, that is, in that country or state or department or province, depending the situation. And then Verra allocates fractions of that jurisdictional baseline, jurisdictional deforestation data set to projects within that jurisdiction. That by itself leads to a reduces the potential conflict of interest, either actual or perceived, and also makes carbon accounting of those projects within the jurisdiction fully consistent among them and with a jurisdictional baseline. So this new approach involves three basic steps from the methodological point of view for baseline setting, for setting the baselines of projects. First, we have to project we need to project the amount of deforestation that might happen in the following years across the entire jurisdiction. Second, we also have to project where that the future deforestation will happen within the jurisdiction. And third, combining these two pieces, where the amount of deforestation that will happen in the future and where that deforestation might happen in the jurisdiction, we should allocate fractions of those data, deforestation data, to projects within the jurisdiction for them to construct their project baseline. That's pretty simple. The first step, basically what we do is to collect using high resolution, high quality satellite imagery and statistical methods. We utilize sample-based area estimation to estimate the deforestation rate that has happened across the entire jurisdiction over the last 10 years, what we call the historical reference period. And then the assumption is that the average rate of deforestation that we observe across the jurisdiction over the last 10 years might hold or might still happen in the following 6 years. That's the jurisdictional baseline. For the second step, we first also construct what we call forest cover benchmark maps, basically forest, non-forest maps at 3 different points of time along the historical reference period, which basically show where deforestation has happened in the last 10 years in the jurisdiction, across the jurisdiction. And again, if we assume that the same processes that cause deforestation during the historical reference period across the jurisdiction might also apply or might also operate in the following 6 years, then we can create a spatially explicit model that shows where the risk of deforestation is higher and where is lower, based on the historical data. Finally, using those two pieces, we allocate fractions of the jurisdictional deforestation baseline to projects that are going to be implemented within the jurisdiction. And that is also a very complicated or pretty complicated step, because there are many different ways in which this allocation can proceed. The first one, the simplest case, is allocated in a very direct, simple, proportional manner. Basically, allocate the jurisdictional deforestation baseline, all the amount of deforestation, proportionally to the forest area in the project area. I mean, for example, if the project area contains or encompasses 10% of all the remaining forest in the entire jurisdiction, then 10% of the jurisdictional baseline would be allocated to the project area. However, that would imply that all forests in the jurisdiction are equally prone to be deforested, but we know that deforestation doesn't happen homogeneously across the landscape. Some parts of the landscape of the jurisdiction are more prone to be deforested, and some others that perhaps are more isolated are less prone to be deforested. And we want to prioritize those areas that are exposed to higher risk of deforestation. So in this new approach, what we do is basically allocate fractions of the deforestation, the jurisdiction deforestation baseline, to projects within the jurisdiction, but directly in a form that is directly proportional to the risk of deforestation within the project area. In this little polygon in there basically try to simulate or mock a project within the jurisdiction. That's basically the main parts of this new methodology, new approach for setting projects, REDD projects baselines in this new approach. And we are convinced that this new approach solves some of the major shortcomings that were found with traditional methodologies. It's a pretty robust approach for that, but implementing in practice these 3 steps has proved very, very challenging from the conceptual and technical point of view. Early attempts that we made back then in 2021, for example, were shown to have a number of shortcomings on the practical side, the statistical side, and so on. Luckily for us, our colleagues from Terra Carbon, from Clark Labs and Clark University began looking into these matters, in particular with this type of projects since 2021, out of scientific interest and basically investing their long experience and knowledge and research that had conducted on these matters. And eventually we began engaging with them formally and asked them for their support, for their help to develop statistically robust methods in order to implement these steps or this new approach. And that's what my colleagues from Clark Labs, Clark University, and Terra Carbon are going to describe in the following presentations. Thank you. You're next.
So we have time for a question for Salvador, as the audiovisual professional will be bringing up Aaron's presentation. Who's got a question? Yes.
When it comes to carbon credits, do you think there will be I don't know if it's just a centralized or uniform way to, when it comes to the regulation of carbon credits? Because in the literature now, it's like everybody has a different way of quantifying carbon credits and all of that. So I'm wondering if in the future you think there will be one way that everybody quantifies carbon credits so it could be profitable and palatable to a lot more businesses and maybe even individuals.
Yes, hopefully that's the idea. I mean, in principle, as I mentioned before, I mentioned at the beginning, the idea is that by having standardized procedures for quantifying emission reductions, they are fungible. No matter where the emission reductions happen, it is 1 ton that is reduced or avoided here or in Africa or in Asia, and also it's completely equivalent to 1 ton that has been released by some polluters so that they really offset. That's the thing. But there are quantifying all these things is very, very challenging from the technical point of view. Doing that in the field is prone to, is loaded with lots of sources of uncertainty that, even for simple statistical reasons, there is a lot of uncertainty and that might not happen. The other one is, yes, different standards and even different initiatives use different data. Perhaps what we have seen, the larger, not discrepancies, but differences, for example, is between those initiatives that are led by multilateral agencies like UN REDD, FCPF, and so on, and then and those that are in the voluntary carbon market. Those protocols in the voluntary, or standards in the voluntary carbon market tend to require, as they operate at the project level, the local level, tend to require and have higher accuracy, higher resolution data than countries have because they operate at the country level. That's one of the main differences with our new methodology. We are collecting data at the jurisdictional level, but high quality, high resolution, the very same one that you would be utilizing or they were using at the project level. So that's another major source of discrepancies. But yes, ideally, I would love to have one single deforestation data set in each country that is used for any purpose. Thank you.
Very good. Thank you, Salvador. Our next presenter is Aaron Meneghini, who's a geospatial professional working for Terra Carbon LLC, where Dr. Dickson is a senior scientist. He's a geographer and remote sensing specialist and specializes in land cover, mapping, targeting, forest extent, health, and condition. Aaron.
Thank you, Gil. Okay, I'm going to wait for a moment while this is set up. Okay, just going to... Here we go. Hello, my name is Aaron Meneghini. I'm happy to be here and talking to everyone. I'll be discussing developing the jurisdictional activity data in the forest cover benchmark maps that Salvador described just a moment ago, both conceptually and a little bit in practice. This is going to be a bit of a high-level overview because these things can get very complicated very quickly, but I want to kind of give you a general idea of how these things work and some of the key challenges that someone who is developing this data might have to face. I'm someone who really likes definitions and kind of clearly labeling the terminology. I'll try to go quickly because Salvador was kind enough to cover some of the terminology just a moment ago. So I'll go quickly through our definitions. I'm going to talk just briefly about how these things are used, and then a little bit about applying this methodology, these components of the methodology for determining the amount of deforestation, and then some key challenges that you would have to face and pay attention to if you were to develop this data. So activity data, as Salvador described, there are, it is about the magnitude of the human activity that results in emissions or removals taking place over a given period of time, your historical reference period, and your jurisdiction. This is taken from VM48 for the Reducing Emissions from Deforestation Forest Degradation methodology, and I've also gone through the GFOI, the Global Forest Observations Initiative, methods and guidance document to take their definition as well, talking about data on the extent of human activity causing emissions and removals over, usually represented as an area. So we're talking about a change in forested area over an administrative jurisdiction over a period of time. A forest cover benchmark map. We can think of it as a wall-to-wall classification where we have all of our pixels in our jurisdiction. Here I have Cambodia, showing the extent and change of forest over the whole jurisdiction for a given period of time. So, if I were to use activity data and FCBM, you're going to use them perhaps in a forest reference emission level, a FREL, or in Vera's new consolidated methodology to estimate your forest change, to estimate your location and persistence of forest change as well. You're going to use them for quantifying the amount of forest loss as a quantity, and then also for your FCBM, perhaps using that map to stratify your samples for activity data, and use that map as an input for your modeling of risk. I will go through this as well quickly. With Vera's new consolidated REDD methodology, we're using this activity data to get our quantity of loss and our FCBM to get our location of loss. When we first start applying this methodology, our first challenge for these things is to define what a forest is, because we need to know what we're mapping and how we're evaluating this. Forests are typically defined nationally, commonly through some canopy cover and height threshold over a given area. Countries may have further qualifiers, such as the underlying land use of the tree-covered area, the growth potential of the trees that are there. So will they be able to reach a certain canopy density or height? Perhaps the species of trees themselves. But that's really more related to whether it's not used as a plantation or the underlying land use. So in the absence of some national definition, you're going to default to the FAO forest definition in the context of ECS. The FAO has a definition of what a forest is. So I've pulled it here. It's very long, and I've bolded the words that I find very important to pay attention to. Forests are natural or plantations with a tree canopy cover of 10% over an area of perhaps 0.5 hectares. The trees themselves should be able to reach a minimum height of about 5 meters. So this will include younger stands that haven't yet met that height threshold. So, now that we've defined perhaps what a forest is, we can actually begin developing our activity data in our FCBM. You might have a workflow that looks something like this, where you as the data service provider, in conjunction with perhaps a local partner, hopefully a local partner, will work on developing some standard operating procedures that will cover your data analysis, your sampling design, your response design, data collection, and your sampling scheme. We're going to then perform our activity data sampling and label our samples for forest persistence and loss. We will have an FCBM that will inform our sampling scheme, as well as help us calculate the area of deforestation. And I will get into this, how these two interplay. The activity data may also inform upon the accuracy of the FCBM itself. So, here's Cambodia, which I'm going to use to illustrate this process. Cambodia does have a forest definition. It was submitted in their forest reference level to the UNFCCC framework. Here we have a forest is a unit of an ecosystem in the form of wetland and dryland covered by natural or planted vegetation. Again, we have a height requirement of 5 meters on an area of 0.5 hectares with a canopy crown of at least 10%. To begin calculating how much loss has happened in Cambodia through activity data, you will draw random samples, whether they're stratified random samples or systematic samples. So you can draw a number of different, design a number of different sampling schemes, but we have to cover the entire jurisdiction. And then label these samples via the historical satellite imagery for change and persistence of forest. You're going to be evaluating also for non-forested areas as well, which will inform upon your omission and commission error, or the omission and commission of deforestation. So, I have drawn up a plot right here with a little tiny black box over there to represent where this one is. This is about 2011 for this sample. I have the Google historical imagery here to show the canopy cover. I will note that plot configuration is not typically standardized. Typically, it is a square. This plot is about 0.5 hectares, has a square. I just want you to bookmark that perhaps it doesn't necessarily have to be a square, but I will just note that. We move on to 2019 in the same spot, and we have deforestation. I've annotated this image with the dotted lines to try to show my interpretation of what is happening with the conversion from forest and the persistence of forest. This is an interesting plot. I think it's worth discussion based off of what this is, given our definition of what a forest is. It has to be a 0.5 hectare area with a canopy cover of 10%. Is this still a forest, or is it deforestation? This is something that you will have to work out in your SOP to clarify the labeling procedure between your interpreters. And great care should be taken while you're doing this, because it can impact the data set as a whole. Once you've gone through all of your points, and you've achieved a precision target for your sample, you're going to tabulate these things in a confusion matrix. Doesn't necessarily have to be the same stratum that are same map classes that are present in your FCBM, but they can be. You're going to then use the reference data for the deforestation column to tabulate how much deforestation is present in your jurisdiction. The FCBM, or whatever stratification map that you used, will impact the strata weight in that final column there in that confusion matrix. This is how we arrive at the quantity of loss in a jurisdiction. The forest cover benchmark mapping, there are a number of ways to arrive at a land cover map. I have not covered them all here. In fact, I have covered none of them here. As long as you arrive here at this forest persistence class, the non-forest persistence class, and your forest loss classes, and 2 time intervals, these are the key classes you will have. I have actually omitted one class that you're also required to have, which is forest regrowth. The map has to achieve an accuracy of between 80 and more than 90% for your forest class for both the user and producer accuracy. The loss class has a range of 60 to more than 70%. And the reason I have broken this out is that it depends on the canopy cover predominant in your jurisdiction. It is pretty recognized that a lower canopy density of forest is more difficult to map than closed canopy forests. They're much easier to map. They're easier to detect a breakpoint in. In areas where we have a very low canopy threshold for what a forest is, it is a greater challenge. And that is why for a jurisdiction that is predominantly an open canopy forest area, you're going to have a lower required accuracy for that map. Now, I have taken just a global data set here to illustrate this. I've generated this map from Hansen to then get us a visual. I have overlaid or underlaid the classification underneath our plot to see how our map aligns with our activity data sample point. To illustrate that great care and thought has to be taken when we're using these activity data to both inform the accuracy of the FCBM and to get that quantity of loss, which is a key challenge for a data service provider to consider. We have to ensure that the labeled activity data is relatable back to that forest cover benchmark map. So in summary, the activity data determines our quantity. We're basing it off of satellite interpretation of sample points over a jurisdiction, following a lengthy SOP. We'll develop a forest cover benchmark map to mark that location of forest loss over some spatial extent and the time period overlapping the activity data itself. And then both of these products are then used together for establishing a jurisdictional baseline through risk modeling. Some key things for a data service provider to bear in mind is harmonizing that labeling protocol for that activity data back to your forest cover benchmark map, minimum mapping unit, aligning your labeling procedure with your forest definition carefully, and then lastly, the holy grail of having an accurate map, which is a very important topic that I cannot begin to get into in this brief period of time. But thank you.
Thank you, Aaron. We have time for a question. As the AV person brings up the next slides, I see there's a hand.
Hi, I was wondering which kind of social biological or ecological variables are part from your activity data, which period of time you take in account to take the data. If you prioritize some variables or another ones, and how do you classify some kind of this, like explain a little more about the activity data of the territories that you implemented the project.
Let me see if I follow, and correct me if I'm wrong. What variables do we consider while we're developing the activity data? Both like either social variables or that's a good question. The basis of your activity data will be these response design protocol. And you're going to be evaluating primarily Google Earth historical imagery for whether something is a forest or whether it is not. However, something that I have skipped over here is that there is your sampling frame, things that you will sample for deforestation to begin with. So there might be areas that are economic land concessions, that are economic or social land concessions that should be removed from the sampling frame because they have some authorized, some legal, documented legal standing for the conversion that might happen in that area. So you want to put that in a different context. So we try to frame where the samples are based off of some of the social variables. I hope that answers or gets close to your question.
Yeah, thank you.
Hi. I can see that the interpreters are key person with you. So, could you tell me what is the average time they spend with you? Because they had some training. They get to concepts and what is time?
Yeah, the interpretation is paramount to act consistently labeling a sample when you have thousands of samples to go through and multiple interpreters to review them is really key to align our what I think is a forest compared to someone else's interpretation of a forest. And to be honest, who is to say that I'm right or they're right? We really prioritize then having a local partner, and we also prioritize having multiple reviewers. So it's not just going to be me looking at a plot, it'll be 3 other people perhaps looking at a plot. And this is something that will probably vary depending on the data service provider. And then we can look at how much I disagree or I agree with someone else and maybe partition that out for maybe I agree more consistently about loss than I do persistence with interpreter X, Y, or Z. It is really critical. There is not a simple answer that I have. So we work, in our experience, we worked pretty closely over a long period of time to do this work.
I mean, the agreements doesn't change every month. The interpreters change every month.
It should be consistently with the interpreter. So, like for a project, we'll have the same interpreter, like team.
Oh.
Yeah.
Very good. Thank you, Aaron. Ron Eastman is our next presenter. Ron is Emeritus Professor of Geography and Senior Research Scientist at Clark University. He's been Director of Clark Labs from 1987 till now, continuing, and Chief Developer of a Adresi Tearset system that has its associated land change modeler. His research is focused on land cover change, most recently in partnership with the Gordon and Betty Moore Foundation and Vera. Professor Eastman.
Thank you. Do I start the... Okay, thank you. Let me acknowledge my co-authors on this presentation. So this is from the three of us, myself, Gil Pontius, who is one of your moderators, and Becky Dickson, who is the other of your moderators. So this is really a presentation from the three of us. So we start with the perspective of jurisdictional and nested REDD. So JNR, as it's abbreviated, serves as a comprehensive carbon accounting and crediting platform that helps entities with forest-related emission reductions activities to nest projects and other site-level forest conservation efforts in alignment with government climate goals at the jurisdictional level. Now, where JNR is not adopted, Vera REDD Plus projects must use the VM48 framework that requires an alignment of project-level accounting with jurisdictional deforestation estimates. So critical to both JNR and VM48 is the ability to explicitly map at the jurisdictional level the risk of deforestation expressed as a density. So a jurisdiction is typically a country, or for large countries it would be something like a state or a province, all right? And we need to be able to map the risk of deforestation and express it as a density, which is the number of hectares of potential unplanned deforestation per pixel. Now, in this particular map, this is the state of Pará in Brazil. It's a very large area. It's about twice the size of France, to put it in perspective. If you look at the numbers in the legend, you'll see that they're very small numbers. That's because each pixel is a 30 meter by 30 meter pixel, which is 9/100 of a hectare. So the expected deforestation values there are very small. But what's important about this mapping is that it allows you a very rapid evaluation by simple summation of the expected deforestation within a project boundary and integration with jurisdictional deforestation estimates. So you can take, as in the inset at the bottom there, a project area, and you can literally just sum up the pixels inside of there, and it gives you a quantity of what your expected deforestation as you determined it from the FCBMs, okay? And then we'll tie this back to Aaron's presentation momentarily. Okay, so VT7 is the project that we got involved with, the we being Clark Labs and Terra Carbon, to help develop a methodology for unplanned deforestation allocation. The allocation being risk allocation. The abbreviation is UDEF-A, and we developed this to support both JNR and VM48. So the protocol has several distinctive features. First of all, it's mapped at the jurisdictional, that is to say country or provincial scale, rather than independently for selected projects. All right, so this was a concept that Salvador brought up in his presentation. It establishes an extremely and very intentionally simple a powerful benchmark model against which more sophisticated approaches can be compared. So I'm going to describe this benchmark, but bear in mind it's meant to be a basic minimum standard from which you are then expected to develop more sophisticated models. Thirdly, it provides an explicit method for the testing of more advanced empirical models that may in fact involve a lot of covariates in trying to understand the areas that would have more or less likely deforestation. And then the fourth feature here is that it is entirely GIS-based. Okay, so let's talk about the benchmark model. First of all, we did a lot of research in different regions in the tropics, and when we looked at explanatory variables, I realized it's hard to read the captions here on that graph on the upper right, but each of those is a different explanatory variable. I can tell only because I'm familiar with this graph when it's blown up. But the first variable there is distance from non-forest. And on the x-axis, you have a unit called the explanatory ratio. If you're interested in how that's calculated, I have a slide for the comments section where we can discuss it. But it's a simple measure that goes from 0 to 100% that talks about its explanatory value. And so in this particular illustration, we looked at distance from the non-forest, distance from pastures, relative frequency of deforestation in protected areas, relative frequency of deforestation in administrative districts, distance from urban, and so on and so on. All right, so we've then calculated the explanatory ratio for each. And when we did that time and time and time again, we found that there was one variable that was extremely powerful. And importantly, it was one variable we knew we would always have, and that is distance from non-forest. All right, distance from the forest edge. And so we start in the benchmark model with this one single variable of distance from non-forest and use that as a single explanatory variable. The benchmark then classifies distance from the forest edge into 30 classes in a geometric series where the classes are small near the forest edge and they gradually increase. And there's a methodology for how you apply that geometric series. We call these vulnerability zones, and you can see that in this graphic where you can see the zones emanating out away from areas of previous deforestation. All right, so that's one component then of our benchmark model. So that's what you're seeing on the left here. That's your 30-class vulnerability map based upon a single explanatory variable. And I know your minds are thinking, why just a single variable? We'll get to the other variables, okay? But this is the benchmark. Then we combine that with a map of administrative divisions. Administrative divisions are useful techniques that jurisdictions use to manage land. They are typically the units in which decisions are made about the allocation of land. All right, so we're going to combine those two to form then a series of modeling regions. So you see the two components that go into it, and they literally superimpose the two in a cross tabulation, and you get then our modeling regions for the historical reference period. So in this particular case, we had 30 vulnerability zones in Pará, the state of Pará in Brazil. There are 144 municipalities, and so 30 times 144 gives you 4,320. The colors look very much like the vulnerability map, and that's only just because of the way in which we combine them. So, for example, you can see that the numbers go up to an ID of 30,144. That tells you you're in zone 30, which is your highest vulnerability zone, and in province municipality number 144. Okay, so now we have several, typically 1,000 modeling regions. We then use that to look at the unplanned deforestation that happened during the historical period. So this is what actually happened during our reference period, all right? The historical period, HRP is the abbreviation. We count up the frequency within each of these modeling regions, and we'll get a table. So you can see this is an excerpt from that table on the right-hand side. So you have your modeling region ID here, and then this is the relative frequency of deforestation. All right, so those relative frequencies are now mapped, You can see the map here on the right, and then also recorded in a table. Now we take that relative frequency table, and now we apply it to new modeling regions for the future. All right, so as we start into the validity period for the project, we're now looking at a new period of history. We're working forward. We're going to take the map of non-forest at the beginning of the validity period. We'll then construct new zones of vulnerability from that, and we'll combine that with the administrative regions to get then a whole new set of administrative regions, and they'll have the same number sequence. And so now become probabilities in the future. And so that's what you see on the right. And these are expressed not as simple probabilities, but they're expressed then ultimately as densities of deforestation. So we take those probabilities, and then now we take the data that Aaron was talking about, the activity data, and those act as a calibrator to now convert that into expected quantities of deforestation per pixel per annum. All right. Now, that was our benchmark. We're expecting jurisdictions to actually try to produce better models. All right. So in order to do this, we need to have some way of testing out whether or not those models are better. So what do? Well, first thing we do is we develop an assessment grid. The assessment grid is a set of grid squares that are designed to be equal to the area of the median size of REDD projects within the jurisdiction. In this particular case, the example here is 100,000 hectares. That was the median project size within Para. I didn't show it here, and I should have, but we weed out all the little intersections with the edge that are smaller than 100,000. We only keep the ones in the center there. Then what we do with that grid is we can actually look at a map of what really happens and compare that to what was predicted. So we'll have two axes. Our y-axis is what was predicted by the model to be the future deforestation. And then on the x-axis, we have the actual. Now, I'll talk more specifically about how we do this in a moment. But once we have that comparison, each dot here represents one of those grid squares and shows the success with which we predicted the future, all right? We then look at the median absolute error as a single index for how well the model performed. And in this case, we can see the median absolute error is 183.44 hectares. That is 183.44 out of 100,000. So that's how you get less than 1%, 0.1%. Where is a median error expected. Okay, so how are we going to do this with alternative models? As I said, the benchmark is only intended to set a minimum standard of quality. Jurisdictions are encouraged, in fact, they're required to submit alternative empirical models that can be proven to be more skillful than the benchmark. So your alternative models can use any number and expression of covariates. Somebody had a question about what covariates could use. It's entirely up to you. You could choose whatever seems to be appropriate for the jurisdiction under question. What modeling procedure should be used? That's entirely up to you. You can use multi-layer perceptron, logistic regression, random forest, whatever technique that you feel can best capture the deforestation. In the current implementation, then, once you have an alternative model, so here, for example, I've taken an MLP transition potential as a neural network model, and it's based upon a whole series of different empirical covariates, I should say. Then we take that and use that as the basis for creating a new vulnerability map. So we use that instead of the single variable of distance from non-forest. Now we use the output from the neural network to develop a new 30 zone map, and at that point it goes through the same process. All right, so our historical reference period goes from T1 to T3, and we divide it in the middle of T2 so that we have, over the entire historical period, we divide it into two periods, a calibration period, the first half, and then a confirmation period in the second half. Those are used for testing, all right? This is how we test whether or not an empirical model is going to be an improvement. And so you can see here at the testing stage, in the blue here, we have model fit for testing. So we take our calibration data, we calculate the deforestation, the relative frequencies, we then project it forward to the confirmation period, and then we do that test with the grid to see how well it did. We calculate the median error. And then we do that again for a prediction into the confirmation period. We do it again for an empirical model. And you can test any number of empirical models you want, but if you select an empirical model, it can only be because it has exceeded the benchmark for both the period of the fit and for the prediction for the calibration and confirmation periods. Okay, so here's an example for Para. I have selected a multi-layer perceptron case with, Rishi may remember, but it was a large set of covariates that we used as independent variables there. And you can see in the case of the fit, we're actually fitting to the data that we know. And so that is typically better than the prediction to the future that it doesn't know, the confirmation period. So you'll see it's always worse during the confirmation. But if we now compare the median absolute error from the benchmark 307 to the MLP model for the calibration period, that's the fit period, it drops down to 183. So lower is better, right? So that's a much better model. So it beats the benchmark then at that point. Now we look at the confirmation period where we're predicting to the future, and we go from 314 down to 298. Yes, it's an improvement. And so in that particular case, it's validated for use. We can say, it's okay, now you may use that model. And jurisdictions would be typically asked to produce at least two alternative models that hopefully can beat the benchmark. The standard sets out in words exactly how to do it. It's a GIS-based procedure. It says, do this, do this, do this, do this. You can implement it in just about any raster-capable GIS software. However, to facilitate things, at Clark Labs, we did create a couple of software implementations, which my colleague Rishi is going to talk about in a moment. One is available on GitHub. It is a Python-based implementation that anybody can freely download. And it simply goes through all the steps that are outlined in the document. And then in the Terra, the new version of TerraSet, coming out in December, it's called LibreGIS. That also has an implementation there. Okay, so any questions?
Hi. My question might be slightly out of topic because maybe I'm mistaken what's the use of that map. My understanding of why you want to predict deforestation risk is that you want to know where your intervention would have the highest additionality and where the carbon could be at best saved. And if that's the case, what's really interesting is your plots, your prediction, for example, here that you're showing us, you have the standard issue where we call mean reversion. Like as you see, your slope is smaller, your OLS slope is smaller than 1, meaning you are over predicting lower values and under predicting bigger ones. And that's the question. If I'm right that you really want to predict well the hotspots of deforestation, is that something you're taking into account in your way you evaluate models, like weighting more like high predictions and errors on the upper tail, or is that not part of the process?
Thank you. Here's the slide. So I anticipated somebody would ask this, and it's a really important issue that you raise, okay? When you plot these things out, what he's referring to is sometimes called regression attenuation. You'll notice that if you plot the OLS line, so this is the green line on these plots, that's the ordinary least squares, and compare it to the one-to-one line, which is a red line, right? Which is a case where you have a perfect prediction of the actual deforestation. You then typically see that there is a bias. So what is the reason for that bias? Trust me, we have agonized over this, but not because it's not something that we should know about, but it's something that we do need to know about a lot. What we've determined as the various causes amongst those, and we don't know how to apportion these yet, but map error is a critical component of this, all right? So when we have an axis called actual deforestation, we don't know actual deforestation. We know mapped deforestation, that's the best we've got, all right? So that we know to be a component. I should have put these in an order. Probably the biggest one that we know of is non-stationarity. That is huge. So you have areas that in the future didn't behave like they did in the past. We see this quite often. We see areas, for example, in the calibration period in Para, there are some regions where we see very little deforestation happening, and the only deforestation that happens is kind of an edge accretion near existing areas of deforested lands. And then you move into the calibration period, and all of a sudden you have these big projects opening up with a quite considerable commercial investment. There was nothing there historically that could have allowed you to predict that because it was not behaving like it did in the past. And so this is definitely a model that's based upon an assumption that the past can tell us about the future, and it can't always. So that is, without question, the biggest one. We don't know how big a contributor map error is, but we know that it's a big contributor. And it's something that we, as a profession, and I use my GIS remote sensing hat on there, we need to really understand this better. This one is a surprise one, model error. Model error is causing variation in the y-coordinate. The y-coordinate should not introduce bias in the regression. The y-coordinate should only increase the variance. So why is it there? And we found this again and again. Not big, but it's there. Well, it turns out that our models are typically based upon covariates, like distance from urban, distance from roads. Well, if you don't have a good map of roads, your map of distance from roads is also not good quality. And so map error creeps into also the modeling process itself. The generality of the modeling regions is another component. All right, so we combined the 30 vulnerability zones with the municipalities. How general they are or how specific they are can vary that bias effect. The size of the assessment grid, as you get bigger and bigger grid cells for the assessment, the error goes down. It's the modifiable error unit problem, right?
May I interrupt you on this? Because I think you always find bias. I think it's a more general property. Like if you do a prediction on something and just use a predicted value on the true value, you always have a lambda, a coefficient lower than 1. The question is more on the finding the right model. My question is it correct that you are interested in a model that predicts particularly well high deforestation zones? And if so, would it make sense to either use a different loss function that gives more weight to predicting the upper tail of the distribution and giving less weight to the lower tail of the distribution? But maybe again I'm mistaken on how we use that data for what's the purpose of the data.
The standard does not set any guidelines for how you come up with the alternative models. All right, so the guidelines only provide a benchmark and just say you must perform at least this well. So if you have a modeling procedure that involves some sort of weighting process, you're free to use it. Right.
I'm thinking about evaluation of the model again. You want the model that best predicts the upper tail of the distribution, but we can talk about this at the end. I don't want to take
No,
time.
it's an interesting discussion. Yeah, definitely.
Thank you, Ron. And our fourth and last presenter in this session is Rishi Singh, who's a geospatial research scientist at the Clark University Center for Geospatial Analytics, where his areas of expertise include remote sensing, land change monitoring, and habitat modeling. He has case study experience across the globe with a core focus in Southeast Asia and South America. Most recently, Rishi has been engaged with designing methodologies to support global voluntary carbon market and developing tools to bring transparency to the seafood industry. Welcome, Rishi.
Good afternoon, everyone. So, as Becky kindly mentioned, this is a bit of an adaptive presentation due to some scheduling things. So, we're going to move very quickly. Luckily, I'm building upon the shoulders of Salvador, Aaron, and Ron, who have done an excellent job of laying out the background, context, and particularly Ron laying out the logic of what I'm going to be explaining. So, I'm talking about the UDEP-ARP. Ron just talked about the UDEP-A, which is the methodology. The UDEP-ARP, the Unplanned Deforestation Allocated Risk Modeling and Mapping Procedure, is the tool that he mentioned in one of his slides. So, I'll actually just skip through this. This is mostly what Salvador laid out, but long story short, we have the UDEP-A methodology, and then to facilitate that, we built the UDEP-ARP. So I'm going to just jump into a case study. So as Ron mentioned, this is the state of Pará in Brazil. This is the FCBM 4 class map that Aaron was talking about that is very paramount to all the work. This is sort of the logical starting point. In the map you can see in the green, you have the stable forest for the HRP period, in this case 2009 to 2018. And then we have in yellow and red the forest loss broken out for the sort of the calibration, the confirmation, that those split dates for the testing. And then the stable non-forest across the HRP. And then we just have a locator map in the bottom right corner. So talking about the software accessibility, the UDEP-ARP is available on GitHub. I have the link there, and we just show a screenshot of the website. So when you go there, you can download all the code, you can download the executable file for the application, and you can download all the resources and documentation behind that. Thinking about the installation, we made it very easy. If I go back to the previous slide, you can see this releases section in the bottom right corner. If you go there from the GitHub, you will be able to find the most recent version of the UDEP-ARP. It's, as you can imagine, is in development because it's very new, so we're constantly revising it. If you go to get it, I recommend going to the releases to get the most up-to-date version. Under the releases tab, we have all the code, but I think the one that most people will get is the UDEP-ARP Windows, in this case 2.11, the setup file. This setup file, if you launch it, it'll guide you through all the installation, and so it makes it quite easy. And as Ron has mentioned, we also have done implementations of this open source tool in other GIS platforms. On the right side, we show an example from Terset Libra, but we've also made plugins for ArcGIS as well as QGIS. And then just thinking about the requirements, I won't go through this too much. I think the important parts are, as of now, it's only supported in Windows. And then I think from a hardware standpoint, the important one to mention is RAM. So all of the processing is happening in RAM memory. So when you think about a project such as Pará, as Ron mentioned, which is twice the size of France, you're going to need substantial RAM to be able to do that. So that's sort of the biggest bottleneck, is having adequate RAM. But the tool is free to use and distribute, so you can get it from the GitHub. So I'm going to go through just a actual case study of this. So thinking about the data inputs, UDEP-ARP is compatible with any sort of raster format data that is either TIFF or .rst. And I think just an important note on the raster layers before you get into doing it in the work. I point this out because oftentimes these things go unchecked. but it's really important and critical to the success of the model that all the rasters are co-registered. So their spatial extent, rows, columns, and pixel resolution is uniform, as well as, I think the second point is the most important one, they need to be in an equal area projection. So things like lat long, it's not going to work because you need to have, there's a lot of distance operations that happen. And so if you're not in a projected area, in an equal area projection, you're not going to get your area metrics correct, and you're also not going to get those distance operations correct. And then uniform masking when appropriate, which particularly comes in play when you consider exclusion zones. So this is our starting raster image. I talked about this before, so I'll just skip ahead. From this one raster image, this FCBM4 class, you can get all of the layers that are necessary, except for the municipalities, or the administrative divisions rather, to do the work. And so just going through the layers, we have our jurisdiction mask, which is a 1-0 Boolean that just shows all the pixels being mapped. And then we have our forest at our 3 time points, time 1, time 2, and time 3. I'm just going to jump back to show that again. In the top right, you can see that this is gross deforestation, which is how it's laid out to be done. And then the distance images, and then the deforestation broken out for those individual time periods, the calibration, the confirmation, and then the combined HRP. And then the administrative divisions, which in this case is the municipalities, which goes from, we have 144 in this area. So the data analysis. So this is the UDEP-ARP tool. When you open it up, you'll see, and I have the slide that Ron had talked about on the right as a reference. So looking at the fitting phase for the calibration, I have the prompt on the left. I'm just going to go through and just kind of show you how you would fill it out. So I won't talk about what it's doing. We'll just go through. So initially, we're going to create the NRT. This is the negligible risk threshold. This is the range at which 99.5% of the deforestation occurs. Past that, you have 0.5%. And so this is used to create the control points that are used for the distance when you create the vulnerability zone. So as Ron mentioned, the output there is a vulnerability map that ranges from vulnerability map that ranges from 0 to 30, 30 being your highest risk areas. And then just a note on alternative models. So we have support in here for alternative models. And to create that, it's the same process, except instead of starting with the distance non-porous, you're going to use the map of 0 to 1 as your control points. And then we create the allocation map from those vulnerability zones. So once we have vulnerability zones, we can then assign the relative frequency from the empirical history, and you get a map that looks like this. So it's very similar, but as Ron mentioned, the range is now from 0 to 30,144. So risk zone 30, municipality 144. And then we have the density image. So this is allocating that relative frequency and then turning it into the density per pixel of hectares of predicted loss. So in this example, you can see that at the most, in this stretched example, it ranges to 0.023, which is a low value, but when you scale it up, they all add up. And then moving across into the model fit. So you can see that it's interesting, none of the prompts are filling in. When you fill in the information here, you can create a map that is used to compare the model. Ron's already described the interpretation of that. And then output from that, which is very useful for people to view to understand their models, we create a residual map. So this just shows where the difference between the actual versus predicted in those assessment grid cells. Moving ahead to the prediction phase. So once you've created the vulnerability zones and done the fitting for the testing stage, you can move on to the prediction, which is where you build upon the analysis you previously done and push it forward into that confirmation time period. And so again, it's very similar. It's still the vulnerability zones, the allocated risk, and then the model fit. And so just moving through that for the prediction, we have our vulnerability zone. And then we create our allocated risks, which I'll show here. We have a trap message. Ron talked about this. The vulnerability zones can shift. And so what happens is the relative frequency, you sometimes can end up with zones that weren't initially there. And so then it has to go through and estimate them from the other relative frequency. And then this just shows the density image. In this case, it does range up to that maximum of 0.09 at 30 meter. And then again, the model prediction assessment. And then that just shows another one of scatter plots. And this shows the residual. So once you've done the testing stage, you can move ahead to the actual, and then you get the review map, which is the same as the FCBM. Okay, once you've done the testing, and typically this comes into play if you have alternative models, you can move to the application stage, which is when it actually gets applied for the crediting. And so again, you have a fitting and you have a prediction stage to this. And so you'll notice that the prompt is exactly the same as before. The only difference is we don't have the comparative assessment. That's because in this example, we wouldn't have that date, that future date, it's because we don't know what the future is. And so we can't do the model assessment. But as you can see, again, you're going to build the vulnerability zones from that distance from force edge. And that's using, again, the negligible risk threshold from the HRP. And then you're going to intersect those with the municipalities. In this case, again, to get those finer detailed modeling regions, and then assign the relative frequency to those. So it shows the modeling regions. And then when you assign the relative frequency to them and then convert them to densities, you get a map that looks like this. So you can see it's different than what we got for the fitting for the testing. And then moving into the prediction phase, I think this is the one that is the most different. Again, we start with the vulnerability map. So taking the distance from the force edge at this point in the HRP, so 2018 in this example, the most future date that we have. Using the same HRP negligible risk threshold, we then bin it to be the vulnerability zones. And that shows the modeling regions again with the range of 0 to 30, 144. And then turning it into that ultimate density map. So, thank you, everyone. Any questions?
You did such a good job.
I guess so.
Yeah. Yeah, well, we just took 2.5 years of work and wrapped it up into an hour and a half. So you guys should understand the whole process, right? So please continue to ask questions. I think this is a really unique situation that I want to highlight where we had a problem, right? That Salvador talked about, where we had a whole lot of different methodologies. We had a lot of criticism about how REDD projects were working. And in response, we pulled in the best science that we knew how to do, recognizing also that science is a continually evolving thing, right? It's a living and breathing thing. And so we've done our best to come up with a very clear, standardized approach that can be applied. So thinking about how you take your science and you put it into action is, I think, a motivating thing for all of us. And looking at Vera as an example where they're open and looking to try to improve our methods, to improve the science. And that's how we're going to get to sustainable land systems, right? It's the only path forward. So thank you to everyone for all of your time here. And thank you to all of you for your work on making this a much better procedure than we had before. And as we put it into action, there will certainly be more criticisms, and we'll definitely find more problems, but look for solutions. Like, that's our job. We have to find the solutions. We can find the problems, but don't just find the problems. Find the solutions to the problems. So, thank you.